Hello and welcome to another topic in chemistry together. Our topic today is molecular structures. So if you are taking these notes during Miss Killinan's Try 3 class in 2021, go ahead and set up your focused note page. If you are watching these notes for any other time or any other reason, I welcome you. Let's learn some chemistry together. The essential question we will be answering during this lecture is, how do I interpret and draw molecular structures? So you're trying to make a stable molecule, you know what elements are involved. What would the actual structure look like if you thought of arranging those bonds and those pieces together? So this video assumes you already know about ionic and covalent bonds and sharing electrons versus gaining and losing electrons, and we kind of build off from there. Pause the video if you need more time setting up your notes. Otherwise, let's get into it. So just to clarify, what we're talking about is this. So this is a structure. These are different structures: methane, water, ammonia. What's with the dots and the lines? How come this one doesn't have any dots? How come, what's going on? So the idea is like, okay, what does this even mean? That's our focus for today. So if we have structures that look kind of like this, dots and lines, so what do those things mean? Let's just focus on interpreting those structures first. So a line means two shared electrons, and that's a bond. So to create a bond, we need those attraction, a pair of electrons from one nucleus and another nucleus sharing those pairs of electrons. That is what creates a bond. So this would be a covalent bond, sharing electrons. The dots are unshared pairs of electrons. Those are also sometimes known as lone pairs, which I know sounds like an oxymoron. How can you be a lone and a pair? But the pair is not shared. So that is what a lone pair refers to. And then also the octet rule is followed. For example, look at this nitrogen. We said that the line means two electrons. So there's 1, 2, 3, 4, 5, 6 electrons on this bonded, and then 7, 8. So this nitrogen has 8 electrons, octet rule. So most elements remember that 8 is the octet rule. A few of them remember sometimes it's only 2, and that's because of the S block versus the P block. So for example, hydrogen only needs 2 electrons to be stable because that fills the first energy level, 1s, and there's no other P sublevel, so it's okay with just 2. So when the S is full, hydrogen is full. That's the exception we're going to use the most. Other than that, generally it's 8 electrons. So like this nitrogen we already saw had 8. This hydrogen only has 2, that's fine, but this oxygen has 1, 2, 3, 4, 5, 6 in that bond, 7, 8, then total 8 octet rule. This fluorine has 1, 2, 3, 4, 5, 6 lone electrons, and then 7, 8 would be the shared, and this hydrogen only has 2. So the idea here is that's when you're looking at a structure, lines are bonds, dots are unshared pair of electrons, but they're there to show how the atom is sharing electrons, what's it bonded to, and then what electrons are just kind of left over on separate elements. Okay, so again, electrons almost always occur in pairs. A covalent bond represents 2 electrons. So that would be known as a single bond. So a single bond is just 2 electrons. Sometimes, though, they have to be more creative in their sharing of electrons. So then you might have a double bond, which is 4 electrons because it's 2 pairs. Or you could have a triple bond, 6 electrons, 3 pairs. So as far as we know, that's the maximum. We don't have quadruple or quintuple bonds. So a single bond is just 1 line. So then a double bond would be 2 lines. A triple bond would be 3 lines shown in the structure between the elements. And then again, that definition of lone pair, a pair of electrons that is not in a bond. It's not being shared between elements, it's just being attracted by one of the nucleus in that structure, in that molecule. Okay, so that's kind of some just like straightforward information about just looking at the structure of a molecule. All right, so go ahead and do a level 1 question so far. It could be about bonds, it could be about structures. You could draw a picture of a structure and point to the line and say, what does this mean? So a level 1 kind of question. Pause the video, take a time to kind of process the notes so far. Come on back when you're ready. All right, so these next little slides, I actually don't want you to write anything. I just want you to listen and watch. So I'm just going to go through a few examples of some structures. No sense in just writing them down. I just want you to listen as we talk through them. So let's use diatomic hydrogen as an example. So the structure for diatomic hydrogen is 2 hydrogens bonded together, but the tricky thing is that's only 2 valence electrons available because each hydrogen has 1 valence electron because it's 1s1, right? So 1 electron. So when they come to make each other stable, each hydrogen brings 1 electron, and they share that pair of electrons, so they both have two. So this hydrogen brings one electron, this hydrogen brings one electron. Obviously, their nuclei are equal because they're both hydrogen. So this nucleus attracts both electrons, this nucleus attracts both electrons. That attraction connection is a shared pair of electrons, hydrogen, one bond between hydrogen and hydrogen. That's the idea. So a single bond makes the whole molecule stable now because this hydrogen has access to two electrons filling the s sublevel. This hydrogen has two electrons filling the s sublevel. Okay, so that's really a very simple example. Same idea though, let's make it a little bit more complicated. How about diatomic oxygen? So we've talked about the fact that O never exists by itself because it's too unstable. It's either in a molecule like H2O or it's O2, diatomic oxygen. It has 12 valence electrons available, 6 from each oxygen, because if you look at the periodic table, it ends in 2s2 and 2p4. So the 2s2 and 2p4, 4 plus 2 is 6. So each oxygen starts with 6 valence electrons, and to make both atoms stable, they create a double bond, and it looks like this. So here's the 6 electrons that this oxygen starts with. Here's the 6 oxygens that this electrons start with. But the point is that if they just share one pair, they would still just each have 6 electrons, and that's not stable. That's not the octet rule. So they're like, well, wait a second. If I put in a pair of electrons for sharing and you put in an electron pair for sharing, we could share 4 electrons and then total, look, 1, 2, 3, 4, 5, 6, 7, 8. So this oxygen has access to 8 valence electrons. 1, 2, 3, 4, 5, 6, 7, 8. This oxygen has access to 8 valence electrons. So now the p sublevel would be acting like it's full. That gives you 8 valence electrons, stable sublevels, stable molecule. That's how they make it happen, sharing 2 pairs of electrons. Same idea, let's continue with this diatomic trend. Nitrogen, it doesn't exist by just an N. It's either in a compound like NH3 or it's diatomic, 2 nitrogens bonded together. But they only have 10 valence electrons available, 5 from each nitrogen, because if you look at the periodic table, it ends in 2s2, 2p3. So 2 and 3 is 5 valence electrons that each nitrogen starts with. But that's not the stable number. 8 is the stable number. So because they have less electrons available, to make both atoms stable, they have to do more creative sharing. So we need a triple bond. So I start with 5 from this nitrogen, 5 from this nitrogen. And they're like, oh, hey, I could put this electron in and then we'd have a pair of electrons sharing, but then I'd only have 1, 2, 3, 4, 5, 6. Oh, well, then I could put another one in and another one in. So now we would be sharing 7. Oh, and I could put another one in and another one in. And then now you'd be sharing total of 6 electrons shared, 3 bonds. It looks like this. So there's your triple bond. So this nitrogen has 2, 4, 6 from the bonded, 7, 8. So this nitrogen has access to 8 valence electrons, filling the S and P sublevel, making it stable. This nitrogen has 6 electrons in the double bond, triple bonds, 7, 8 electrons total. So this nitrogen nucleus has access and is holding on to 8 total electrons. Creative sharing to make, since there's only 10 electrons available, this is what you have to do for each to have access to 8. So that's kind of some visual examples and some chemistry of what's going on, sharing electrons, creative ways to be stable. Going into a level 2 kind of questions. I know we didn't write any of those middle notes down, but you can still either write a question about them or do a level question about the level 2 questions about the notes you already did write down. Okay, pause the video, think about the notes we've taken so far, process them a little bit, take a little break. Come on back when you're ready. So the next piece of the notes then, so you've talked about structures, I've shown you some examples, now it's time to actually do some. So how do we draw structures to represent these stable compounds? So if there's only ions, think of the ones we did like on the Lewis dot diagram day, like last week or earlier this unit. You automatically give the elements the 8 dots that they have. You put a bracket around them, and then you put the positive or negative charge that happened to get the 8 dots. Like remember we talked about fluorine starts with 7, so you need bracket and a -1 to give it the 8 dots, right? And then when you're drawing, you put any positive brackets next to negative brackets to show that they're losing and gaining to each other. Okay, but what about if it's just a covalent bonding? So it's just a molecule. So this is the part that's new. Add up all the valence electrons of the elements involved. You look at the periodic table for that. Make at least one bond between all the elements. Why? Well, they wouldn't be a compound if there wasn't at least one bond present. Then you add in the lone pairs or multiple bonds that are needed to make each atom stable. And remember, it's generally the octet rule, except hydrogen only needs 2 electrons. So you think of it kind of like a puzzle. So I know there's at least one connection between everything, but then where are the rest of the pieces? Are there lone pairs? Are there double bonds? All of that stuff to make each atom stable. And remember, stable means every element has 8 valence electrons accessible to it, or hydrogen is one of our exceptions, it only needs 2. All right, so let's take a look at some of this puzzle piece putting together. So let's go through those same numbered steps that I just had on the previous notes. Let's do dichlorine monoxide. So dichlorine monoxide. Step 1 said if they're ions, oh wait, but there's no ions present here. These are nonmetals and nonmetals. You could look up their electronegativity values. They're pretty close together. So your 2 nuclei are not strong enough. One of them is not strong enough to compared to the other to take any electrons away. So they're sharing instead. So skip step 1. Step 2 says add up the number of valence electrons. So chlorine is right here. Go back to the beginning of the row. So there's 1, 2 in the S block, and then 1, 2, 3, 4, 5 in the P block, meaning S and S2P5 would be 7 valence electrons for chlorine, but there's 2 of them. And then oxygen, so again, go back to S and P, 1, 2 in the S block, and 1, 2, 3, 4. So S2P4, that's 6 valence electrons for oxygen. So each chlorine has 7 valence electrons. Oxygen has 6, so add it up. There's 20 valence electrons available for the whole molecule to be stable. None of them are stable right now, so they're like, hey, we got to do some sharing. I want to have some elements, or I want to have the right number of electrons. I want to be stable. So the next step says, okay, well, they've got to be connected to each other. And it turns out in the natural world, things try to be symmetrical if they can. So instead of chlorine sharing with chlorine, those 2 nuclei are pretty even. Oxygen is going to get in the middle of them, and we're going to make a symmetrical molecule. So just know that that's generally your first choice if you can be. Make a central atom, something that's in the middle of things that are opposite each other, right? So we have 2 bonds to start, an oxygen and a chlorine, an oxygen and the other chlorine. So there has to be 2 bonds, otherwise you wouldn't be able to connect all of the elements. So that's 4 electrons so far of the 20, so I've got 16 left. Remember, these 3 dots mean therefore. So the next option would be just spread around those 16. So this chlorine has 2 right now. So 1, 2, 3, 4, 5, 6 more. This oxygen has 1, 2, 3, 4. So 4 more. 1, 2, 3, 4. This chlorine needs the same as this. 6 more. 1, 2, 3, 4, 5, 6. So 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Oh, hey, it works out. I have 16 electrons that are just spread out. 4 electrons in the bond. That equals the 20 valence electrons I had available. So I check. Does it work? Yeah, it does. Are all the atoms stable? Well, this chlorine has 1, 2, 3, 4, 5, 6, 7, 8. That's good. This oxygen has 1, 2, 3, 4, 5, 6, 7, 8. Oxygen's good. This chlorine, 1, 2, 3, 4, 5, 6, 7, 8. Yep, chlorine's good. And then do we only have the number of electrons available? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Yep, all good. So this is the stable structure for dichlorine monoxide. All right, let's try another example. How about this one, SO2? So once again, it's not ionic, so I'm going to skip that step. How do I know it's not ionic? Nonmetal and nonmetal, or look up the electronegativity values. They're pretty close together, so neither nucleus is strong enough to actually take electrons away. So I skip step 1, I go to step 2, which is where I add up the valence electrons. Well, it turns out that sulfur and oxygen are in the same column, so they're going to have the same number of valence electrons. S2 and P 1, 2, 3, 4. So they're going to have 6 valence electrons each. So sulfur brings 6 and both oxygens bring 6, right? So total, I have 18 valence electrons available for the whole molecule to be stable. None of them are stable right now, so they're going to have to do some sharing. All right, so that means step 3 is to make bonds, and if possible, we do a central atom. So sulfur is going to go in the middle to make a symmetrical if possible. I've got 2 bonds now, 4 electrons. Oh, but now I only have 14 electrons left. Okay, well, if I just spread out and make everyone stable, look at, oh, wait a second, but this is like that example I just did before. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. I have 20 electrons and there's only 18 available. So this structure does not work. So look at, I X'd it out. This does not work. So I have too many electrons in my picture, which means I need to do more sharing. So how about a double bond somewhere? Let me try that. So now I have 3 bonds used. 6 electrons used, only 12 electrons left. Let's see if we can just spread it out. This oxygen has 4 already, so it only needs 4 more. 1, 2, 3, 4, okay. The sulfur, look, already has 2, 4, 6, so it only needs 2 more. And then this oxygen would need 6 more, because this is only 2. So I use 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, so that works. So let's look at our structure. This oxygen has a double bond and 2 lone pairs, so that's 8. The sulfur has 1, 2, 3 total bonds and then a lone pair, so that's 8. And this oxygen has 3 lone pairs, 1 bond, that's 8 valence electrons. Okay, so all the atoms are stable. Let's check to make sure we only use the electrons available. 2, 4, 6, 8, 10, 12, 14, 16, 18. Yep, that's what was available. So because there was less electrons available than that previous example, I had to do some creative sharing. And just so you know, for pre-AP Chem, it wouldn't matter if you put the double bond here or the double bond on this side. It turns out that there's different ways to figure out which one it is. We generally think, we being the science community, is that they kind of flip back and forth, right? The electrons are constantly moving around this whole molecule. And so it just turns out that sometimes there's kind of a 4 electrons here, sometimes there's 4 electrons here. So sometimes there's 6 electrons here, sometimes there's 6 electrons over here. It's kind of all swarming around. But in general, this oxygen has access to 8 valence electrons. This sulfur has access to 8 valence electrons. This oxygen, access to 8 valence electrons. It all works, they're all stable, and we only use the exact number of electrons available. This is the stable structure for sulfur dioxide. All right, let's try one more. How about this one? The carbonate polyatomic ion. Okay, so there's something different. So it's an ion, but it's not ionic bonding. So that's interesting. It's also not a stable molecule yet, right? Because it's still an ion. It would need to bond with something that has a positive 2 charge, but I'm not looking for that yet. For now, I just want to draw this structure. Carbonate, CO3, with a -2 charge. So I need to look up the number of valence electrons for carbon and oxygen. We've done carbon or oxygen a couple times. It's S2 and then P, 1, 2, 3, 4, but then there's 3 of them. So it's S or oxygen 6 valence electrons times 3, plus carbon has S2 and then P2, so 4 of them. So carbon has 4, each of the oxygens has 6, so 18 plus 4 is 22. But remember, it's not just that, right? There's also this -2 charge. And remember, a -2 means you are more negative than normal, which means you have more electrons than normal. So it's the 22 electrons plus 2 more. So really, you have 24 electrons for this whole molecule. But instead of calling it molecule, we're going to call it a polyatomic ion to remind ourselves at the end. See if you can think ahead. At the end, we're going to have to put what around our structure because it's an ion. We'll come back to that, but you see if you can predict it. All right, now we do the rest of it like normal. I know that there has to be 3 bonds. How? Because there's a central atom, and then I put those 3 oxygens around it. So to make a molecule, a compound, there has to be at least 3 bonds. That's 6 electrons because every bond is 2 electrons, meaning there'd be 18 electrons left. Okay, so I've got 6 right now, 18 left. Each of the oxygens needs 6 more, and this carbon needs 2 more. Well, wait a second. I already know that's not going to work because 6 times 3 is 18. That would already be my electrons that are left, and I would still need 2 more. Okay, so if you need more electrons than you have, you need to do creative sharing. So how do we do that? What do we do for creative sharing? Yeah, we need a double bond somewhere or triple bond if needed, but we can make this work with a double bond. So I put a double bond in there. There's 2 more electrons of my 18, and then that means that now this carbon is all good, and this oxygen only needs 2, 4 more. So now this oxygen has 8 valence electrons. This carbon has 2, 4, 6, 8 valence electrons. This oxygen has 2, 4, 6, 8 valence electrons. This oxygen has 2, 4, 6, 8. But then notice what I did. Brackets and a -2 charge to represent the 2 extra electrons that have to be gained in order for this to be possible. So don't forget about that. So brackets and charge to make it an ion. And then we just follow our rules. Are all the atoms stable? Yeah, we just check that. Do we only have the number of electrons available with the charge? So 22, let's check it. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 20. Wait, did I miscount somewhere? Oh, yeah, sorry, 24 electrons. Yeah, yeah. So good. That was good for me to make that mistake in front of you because then you will know not to do it. So remember, there wasn't 22 electrons, there's 24, which is what I ended up counting. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. But that is the number of electrons available because this has a -2 charge. So then, just to kind of foreshadow where we would be going with this eventually, so then this is the structure for carbonate, brackets and -2, means that it has to gain electrons from somewhere. So then what I would do is I would find maybe like, for example, barium, and I'd put Ba with 8 dots around it, a bracket, and a +2. Or maybe I do lithium, Li with my 8 dots, brackets, and a +1, and then another Li, 8 dots, brackets, and a +1. So then +1 and +1 would balance out the -2. And then that would be the finished structure of whatever ionic compound this was, instead of just the polyatomic ion. Okay, so there's a lot to process there, lots to think about. So write a level 3 kind of question, and then you'll do a summary too. Level 3 would be some sort of like predict what this would look like in 3 dimension. You could defend why this is useful in chemistry to know the structures. So some type of level 3 question. Pause the video. Come on back when you're ready. That is the end of this day of notes. So here's your to-do list. Finish any Costa questions if you didn't finish them during the video, and then write your summary so that you answer the EQ for today, process what you just learned. I do have an assignment that's related to interpreting structures and also drawing structures, so the 2 parts of these notes. You could also do the unit practice problems, check your answers, they go in the back of your notebook, just a chance to process this new stuff, and you get immediate feedback to see if these new things made sense. All right. And then we will see you at our next Zoom meeting. Thanks for joining me today, learning more about structures and molecules and chemistry. See you next time.